This is the release video for the MicroPad Release 2. Stay tuned. Hey, this is Andre. If you know me, you know that the Commodore PAD is one of my most favorite machines of the old Commodore computers. I have built replicas before, and when the MiniPad came out, I found it's good to see that there is an increased interest in that machine in the community, but feature-wise, I was not so impressed. So I finally set out to build what was on my list for way too long, and that is a modern type PAD extended replica. So here it is, the MicroPad. In this video I've set chapter mark, so you can get to any section you want to see again. And now let's get into it. So here is an overview on the MicroPad. The MicroPad basically is this Eurocard sized board. And if you know Commodore computers, you may notice that this here is the an IEEE 488 cable going down, and this looks like an looks like Commodore tape connector, but that's basically about it. So all the integration density, it has all been greatly increased, speed has been increased, memory size has been increased, and so on. So let's have a look at some details. On the right hand side you see these three I/O chips. Those are exactly the same I/O chips that you can have that you can find in a Commodore PAD. One versatile interface adapter VIA and two parallel interface adapter PIA. Exactly the same. There is some extension. You can actually use this also as a floppy disk drive if you jumper it. Yeah, something I do sometimes. Then there is the CPU. This is also brand new, and you can buy all of those from Western Design Center in PLCC package and in the usual 40-pin DIP package, but for space reasons I have used PLCC here. They all run on rated up to 14 megahertz of clock frequency. I'm running them at 12.5 megahertz clock frequency. You can see here, this is this way. This is a VGA output. So the system outputs VGA graphics in 640 by 480 at 60 hertz. And that's one of the reasons I needed to have this higher clock frequency. There are two memory chips, those two here, each 512 kilobyte of RAM. I'm going to talk about that later in the video. And this chip here is the glue that keeps it all together. It's a CPLD, a programmable logic chip that I used to do all the video output, to do the integration between the different chips and so on. What you're gonna miss here is the classical type of ROM, read-only memory, where the main program, the BASIC, is actually stored, and this is because I have replaced this with an SPI flash ROM, which is just this 8-pin chip, and the CPLD uses a SPI interface to do an initial program load from the SPI flash chip into the RAM before it actually starts the processor. Using the SPI interface of the CPLD, I can actually use it to integrate an Ethernet connection, and below that there is a USB connection. And here in this on this connector here, there is place for an adapter for SD cards. So it basically has pretty much the modern type of interface. And this very small, I don't think you can even see it here, is a real-time clock chip that is battery backed up. if you connect the battery here. This here is a keyboard. I built it from a design by Steve Gray, and I designed all my custom keycaps, as you can see here. I guess I still have to paint them, but it's very, very nice to have a really nice pet-like keyboard here. But you can actually use, because there's a second connector here, you can use a Commodore 64 keyboard just as well. There's the power connector here for 5-volt power input. There's a reset button next to it. Probably can't see it on the camera. Here is an audio output, which I have fed into this VGA to HDMI converter here to actually grab that on the PC. So that's the overview of the MicroPad. Now let's get into the details. Here you can see an overview of the architecture of the MicroPad. In fact, it is actually rather a simple design. Here on the right hand side of the CPLD, you have basically the processor 65816 and the 3 I/O chips that I already mentioned, plus 512K of fast RAM. They all connected to the same data lines and to the same address lines. The only thing is the fast RAM has some more address lines than the CPU has, so those are provided by the CPLD. On the left hand side, there is the video RAM, VRAM, also 512K, connected to its own data bus and its own address bus. The reason for this is that the CPLD is capable of accessing the video RAM while at the same time the CPU is using the bus on the right hand side on the CPU bus to actually access I/O or fast RAM. So those two RAM chips can be accessed in parallel by video and CPU, and if the CPU is using the fast RAM, and that's why it's called fast RAM, it's not being slowed down by video access, like say bad raster lines in the Commodore 64. The CPLD then does the video output generation and produces a VGA video output. Also, the CPLD is providing some I/O registers and provides this SPI bus, serial peripheral interconnect, I think. And there we have the flash boot ROM. As I said, the CPLD on power up takes 256 bytes from the flash boot ROM and stores it into the video RAM and lets the CPU boot from there. And then we have a MAX3421 USB chip. We have an ANC28J60 or something like that, Ethernet chip, which is on a breakout board. I have a real-time clock and non-volatile RAM chip that is backed by a battery. And we have a separate connector for an SD card adapter. So basically that's it. A real fast pad here on the right hand side, some VGA output, VGA card more if you will, on the left hand side, and some modern SPI interfaces. That's it. Let's now have a look at the memory map of the MicroPad. Basically, there are two RAM chips. One is called FRAM or fast RAM. One is called VRAM or video RAM. Both are 512K. So each of those has 7 banks of 64K. I've only displayed the lowest 2 of them because they are the most important. So in the fast RAM, we have the lowest 32K of RAM, as there is in the fully built Commodore Pad with 32K RAM. Then we have another set of 32K RAM with an I/O window where the pad has, of course, its I/O at E800, and there's one page of I/O window like the newest model of the pad had. So you could also have some kind of extended editor ROM in the upper half of the E bank. And what's special also is there you can actually map 4K of RAM from the video RAM to this window, 4K window at 8000 hex in the CPU. So the reason for this is, of course, because there the Commodore PAD has its character ROM video memory. You can actually map that to any of 4 locations located in the character window that is available to the video chip on the micropad. There's only an 8K video memory available for the characters, but you can move the character ROM or the high res in the whole first bank of the video RAM. In bank 1 of the fast RAM, we have the 4 banks of the 8296 extension memory. They are being mapped into the upper 32K of the bank 0 of the Commodore PAD, because that's what the 8296 models do. Well, that's basically it, except for one exception. There is no ROM. So how does the machine boot? The machine boots in that the CPLD reads 256 bytes from the flash memory and writes it into the video RAM, because the CPLD can only write to video RAM. It doesn't have the capability, it doesn't have all the address bits connected or enabled for output to write into the fast RAM. So it writes it into the uppermost page of bank 0 in the video RAM, and then there is a boot configuration that actually swaps the 2 video chips in the memory configuration. So when in normal mode, the FRAM is the first 512K from bank 0 to bank 7, and the video RAM is from bank 8 to bank 15. During the actual boot, it's vice versa. So video RAM is bank 0 to bank 7, and then bank 8 to bank 15 on the fast RAM. But the first thing that the boot code does is actually switch over that, copy itself over into fast RAM and switch that over into the normal configuration. Now we look at the video properties of the micropad. So we start with the 40 column mode, and we look at the video control register at hex E000, which means 59392 in decimal. So the micropad has a number of cool video features that can be easily switched by a simple poke. And just let me show you the first one, which is this one. Come on. Bang, we have a high-res mode. And this high-res mode is basically available in all other video modes as well, with all other resolutions. So you can use it whenever you like, in whatever resolution you like, which I'm going to show you next. But first, let me switch off high-res. Okay, so the next one is, of course, and we may have seen it, this system also runs in 80 column mode, and that is also very simple. You just poke in 2 here, and then we have 80 column mode. note that the memory below, or the lower part of the screen is still displayed. It just has been cleared off before. So let me just fix that for you. Okay, as you can see, poking into the screen area behind the actual screen works, and it's displayed. So let's switch that back again. Let's go here, and bang, we're back. So the next mode is the interlace mode that I want to show, and you may have seen or may see that the text is a little bit gray on that display, and if the resolution is fine enough on the YouTube video, you can see that only every second raster line is being displayed. That's the interlace mode. That's how it looks on the original cathode ray tube monitor that the pad has. So that's the default, but you can switch it off. And now every single raster line is displayed with character data, and you can immediately see that the brightness goes up quite substantially. But well, it doesn't really look like the real thing anymore. It just looks like recreation. But it is, but it helps on situations like that. Then there is another mode that we can do, and I'm only showing it together with this one because now every two raster lines show the same data. So two raster lines show the same data, then the next two raster lines show the same data, and so on. You can switch that to single raster line display, and that suddenly gives you a 50 row display mode, which is quite nice, I think. It only works, of course, if you have a screen that is large enough that you can actually read it. So, and then let's combine that with the 80 column mode, and suddenly you have an 80 by 50 screen resolution. Isn't that nice? So then let me show you something else. As you know, you can print some control characters to switch between graphics and uppercase mode. So you can do something like this. To switch to lowercase mode. And what you also may have noted is that the height of the characters has increased. And that is because a character now has 9 raster lines. In the original, it's 10, but 10 raster lines with 25 lines does not fit into the VGA output. So I restricted it to 9 raster lines. And you can switch it back. And what you may have noticed right now is that the screen went black for a moment because the video grabber had to resync with the output signal, and that is because when you change the height of the characters, the sync signal moves, and the output, the monitor, has to resync, and that sometimes ends up in this artifact. And you can prevent that, for example, in a program or game or whatever that uses that maybe for some effect or so, by just poking this value here. You immediately see that the text starts at the top of the screen, and then you can switch between the modes. And there is no delay or no flickering on the screen. So, and the last thing, of course, is to switch the graphics off. And that concludes the graphic display discussion. So let's have a look at the execution speed of the MicroPet. So we start it up in 80 column mode and load the benchmark. And we can run it. And it's now calibrating itself. So what we have to understand is that because of the VGA output, the timing is rather fixed. So we have 640 by 480 at 60 Hertz resolution, and the pixel clock thus is, it should be 25.175 megahertz, but we're using 25 megahertz. So we end up with almost only 60 hertz screen frequency, but we have 59.5 hertz. So that makes us gives us 16,800 around cycles per screen if the CPU would run at 1 megahertz. As the main clock is half the pixel clock, so we're running the CPU at 12.5 megahertz. We end and we throttle the CPU to 1/12 of that because that's easier to count than 12.5. We run at 1.04 megahertz and we expect around 17,500 cycles per screen. So this is the reason why the 8296 the test program gives us a fault on the 50 hertz screen refresh. I mean, it's 60 hertz versus 50 hertz anyway. But this is why this is deviating from the 16,000 cycles per screen at perceived 1 megahertz. But that is what we're counting against. Then we have the second one here, which is running a loop, and this loop is timed with the VIA register, with the timer register, so that we can count the cycles that the loop takes and compare that to the cycles that the timer register in the versatile interface adapter, the VIA, counts, so we can detect wait states that have been injected into the CPU. So let's have a look at the basic speed properties. We have 4 different settings for the speed. We have 1 megahertz, we have 2 megahertz, 4 megahertz, and full speed. As I said, we have 1.04 megahertz actually at the base frequency, so it's 2.1, 4.2, and full speed is 12.5 megahertz. So because this is VGA output, and we have the VGA output stealing cycles from the CPU, we can test the different types of RAM that we have. We have fast RAM and video RAM, depending on the different types of output properties settings. So the main thing is that this display now is running at interlace mode. That is, every second raster line is output only. So we have that nice warm feeling of some kind of real tube CRTC cathode ray tube monitor with as the pet has. But we can switch that off, and this is what it interlace off is saying. And then every line is output, and that means doubling basically the amount of memory accesses from the video. Also, we can switch the screen off to achieve full speed. Looking at the output from the fast RAM, you can see it doesn't matter. The fast RAM is decoupled from the video, so it always runs at 12.5 megahertz. You may have just seen the interlace switching off and on again when the video became a little bit brighter. You can see it here. With 4 megahertz, the system doesn't care about any video secret stealing cycles, because there's enough memory bandwidth to accommodate for that. But if we run the CPU at full speed, we see that we get some slowdown. So if we have the normal video mode, we lose about 1 megahertz of top speed, and if we run with interlace off, which means twice the amount of data taken from the memory by the video circuit, we lose about 2 megahertz. But that's basically okay. And the reason for this is because in contrast to the original 6502, the 65816 used in the micropad has a qualifying output that says when a memory access is actually valid. There are a number of cycles that the CPU uses internally and is not accessing memory, and the CPLD, the logic on the micropad, just injects the video cycles into those empty cycles of the CPU. Actually, it's the other way around. The video circuit leaves some slots for the CPU, and the CPU cycles are injected there. So even though basically half of the cycles are reserved for video during the raster line output, and only half of the cycles are reserved for the CPU, the slowdown is way less than the 50% we would expect. So cool, even we're running at 12.5 megahertz, and even on the video memory, it's not that much slower. So let's look at the ROM options for the micropad. When you start it up, you get this boot menu that shows you the options that you have on the micropad. You can see that you can use a basic 1, a basic 2, or a basic 4 machine. Basic 1 was the more or less operating system and basic that was initially provided with the original Commodore PET. And it was even so that it was buggy in that it could not actually access the IEEE 488 disk drives. Basic 2 is a very, very common version, and most of the Basic 1 pads have been updated to Basic 2. There are some games that only work on Basic 2. Basic 4 is more or less the latest version, and you can get it in 40 and 80 column versions for the 4032 or 8032 models, or even the 8296 model that has additional 128 kilobyte of RAM. What you can see here is there is the option to use a Commodore 64 keyboard. It's only available on the Basic 4 models because they are using special extended editor ROMs provided by Steve Gray on his website. So there is a keyboard scanner available for Commodore 64 keyboards. And the boot menu actually automatically detects which keyboard you're using by which key is being detected, because the 1, 2, 4, 6, and 8 keys on the N-type Commodore PET keyboard are in different places than on the C64 keyboard. But C64 keyboard option is not available for Basic 1 or 2. Also, there is the option to use extended or patched ROMs. As I said, the Basic 1 had a buggy IEEE 488 interface code, was not able to access the disk drives. If you just use the 1 key to select Basic 1 model, you will get a patched version of Basic 1 that is actually able to use the IEEE 488 disk drives. The Basic 1 also is using the original character ROM, which is different from the later models, and that could easily be seen when you switch the character mode. So what you can see is that only the lowercase characters are being switched to graphics characters, which is different from the newer models. So let's get back to the menu. On the basic 4 models, you have the option for an extended ROM, which you can see like this. And then you see you have a custom editor ROM that has a wedge built in. So you can, for example, access the directory like that. It also has the option to use the left shift key and the @ sign to switch the upper and lowercase modes, like so. And it also has the option to use the left shift, @ sign, and right shift and delete key all together to get back to the MicroPet boot menu, which comes in very handy. If you use the left shift button together with the 1, 2, 4, 8, or 6 keys here on the boot menu, you get the original ROMs. So Basic 1 is not able to use the IEEE 488 disk drives anymore, and the Basic 4 is just the original Basic 4. Like so, you can see the boot message, and trying to use a wedge will give an error message. So let me show you one small program that is using the extended memory mapping capability to give you basically 4 pads in one. Seemingly nothing has changed, but you can now use the 2 keys next to the space keyboard to switch between the 4 different pads, virtual pads. Second one is booting. You can use it. The third one is booting. You can use it. And the fourth one is booting. You can use it. And then you can cycle back to the first one, the second one, the third one. And this is actually not hanging because the key right of the space key is a scroll lock key that is used in that switching sequence. You press off reverse and then the printing continues. So that is actually a nice feature, because if you have something running and printing, it's automatically stopped when you switch back. And that's that. So in this video I've shown you the MicroPet. I've given you an overview on the system and its features. I'm sure there are some room for improvement, like I'm looking into color output for the VGA. Also, you may have noticed those custom keycaps are not exactly the best ones and should probably be replaced with factory-made ones. So one of the main questions that will be coming is, where do I get one? So I'm not selling them, I'm not building them, I don't have the time to do that. However, all of the specs, everything that you need to do to create this machine is on GitHub. You can find all the specs, the code to program the CPLD, the flash ROM, the schematics, everything, the board layout, everything you find on GitHub, and also the docs how to program it and so on. Link will be in the description. I hope you like it. Leave your comments down below. Thanks for watching and see you next time.